So firstly, to introduce the problem we want to tackle, so it has been mentioned, I think mainly on Tuesday morning, that there is this problem with building such a massive piece like supermassive black holes at high redshifts, but like 7 and higher. But to make things even worse, there are some Lyman alpha observations, particularly some measurements of the Lyman alpha near zones, or proximity zones, that have been found to be 1 proper megaparsec or even less. And if you take this at a face value, these are consistent with the optically UV bright lifetimes of 10,000 or 100,000 years. And this is definitely not enough time to build supermassive black holes of masses like a million solar masses or more. So these are Lyman alpha observations, Lyman alpha forest observations. We want to tackle this problem with 21 centimeter forest signal. So to introduce what the 21 centimeter forest signal is, it's a series of absorption features in the spectra of distant radio loud sources, like radio loud quasars. For example, a good target would be the blazer that Studia Baladika mentioned a couple of days ago. So these features arise from the intervening neutral hydrogen structures due to the hyperfine structure of the neutral hydrogen atoms. And as you can see here, you see these absorption features, and okay, it's on. So you see that they arise from the gas that is, somewhat overdense, but mainly neutral and cold. And this is different from the Lyman alpha forest because this one you would see in the hot and ionized gas, so we would draw very different IgM. And another difference is that this is in radium. Okay, so if we have some line of sight through the IgM at the redshift 7, and we have no quasar that, okay, we have a background quasar, but it hasn't been on for a very long time. So we have just the effect of the IgM. In blue here I show a synthetic or simulated 21 centimeter for a spectrum, and in green that's the Lyman alpha for a spectrum. You don't see that because at the redshift 7 the gas will be significantly neutral, and yeah, so that's why it will be opaque to the Lyman alpha photons. So this has been modeled using the Sherwood-Relics simulations. And if we turn on the quasar for, let's say, 10 megayears, we model this by using 1D radiative transfer simulations. This is what happens. So you start to see the Lyman alpha forest here, and this is because the gas close to the quasar is ionized to the levels high enough that it will be at least partially transparent to the Lyman alpha photons. And on the other hand, you see that the 21 centimeter forest here is suppressed. Okay, so to quantify the extent of this near zone close to the quasar, what people usually did or are doing is that, okay, you smooth it with the Boxcar with 20 action, the Lyman alpha forest, and then when this falls below 10% of the transmission, this is where you define your R Lyman alpha, so the extent of the near zone in the Lyman alpha forest. So we did something similar for 21 centimeter forest. So we smooth it with the Boxcar up with 5 kilohertz, and then we say, okay, if this goes below 99% of transmission or 1% absorption, this is where we define R21. Okay, so this is the terminology, but let's look at what is actually happening here. So in this animation, you see in the top panel how the UV photons ionize the surrounding gas. You can see here this ionization from how it propagates through the IgM, and this is nicely mimicked in the green by in the Lyman alpha forest. You see how it propagates as well. However, there is the 21 centimeter forest is a different story because you see in the middle panel here, that's the temperature of the gas. You see also the ionization front here, but you also see this tail of higher temperature beyond the ionization front. And this is just because the X-rays heat up the gas beyond the ionization front because of the long beam free path. And this is what extends the extent of the R21 or 21 centimeter forest signal. Okay, and to look at this in more statistical way, let's put it that way. We did it for 2,000 lines of sight. So the solid curves correspond to the different redshifts, and the shaded regions are just 68. Solid curves correspond to the median value, and the shaded region is just 68% scattered. Different colors correspond to different redshifts, and you clearly see these differences between R11 alpha on the left and R21 on the right. But what is important here is also that if we go back to our problem, you see that you can reproduce, or you can get the small R11 alphas if the quasar is 100,000 years old or less. However, there were some studies that suggested some different models to alleviate this problem, in particular flickering quasars. So instead of having this light bulb model of a quasar of constant luminosity, you will turn on the quasar, then you will turn it off, as you can see here in this plot. So now it's off, now it's again in the bright phase, and so on. And of course, this will affect both R11 alpha and R21. So let's look at that. So in this off phase or faint phase, you have no UV photons coming from the, or low amount of UV photons coming from the quasar. So the gas will recombine. So it will increase its neutral fraction, and this happens on relatively short time scales, and therefore R11 alpha will decrease. And then when you turn on the quasar, it will increase again. It is very different for R21 because, like I said, this is given by this higher temperature tail. And if you turn off the quasar when it enters the faint phase, the gas will cool down, but adiabatically, and this happens in very long time scales, might be longer than the quasar lifetime itself. So in these faint phases, R21 doesn't really change much. Okay, so I should have said that this is for this toy model of homogeneous IgM, but if you do it for more realistic IgM, I should have said that this means that R21 is not sensitive to only the latest bright episode or accretion episode of the quasar, but it is sensitive to the integrated lifetime of the quasar. So this is an important difference. Okay, so if you look at the inhomogeneous IgM now, and again we did it for 2,000 lines of sight, but now different colors correspond to the different ages of the quasar, and the horizontal axis is not the quasar lifetime, but the current episodic time. So basically, since the quasar has entered the bright phase, the latest bright phase. So if you look at two cases of young quasar in blue, so this is the quasar that has just turned on for the first time, and in orange, this is a case of very old quasar which has been flickering for a while, so it has gone through a couple of these bright and faint phases. And now it's like 10 mega years old. You see that in the R11 alpha case, you see that we can still reproduce these small R11 alphas in both of the cases of these very different cases of young or old and flickering quasar. However, for 21 centimeter forest, you see that this is very different. So if you have old quasar, you will just have large R21, even if the quasar is flickering. This is again just because that the R21 is sensitive to the integrated lifetime of the quasar rather than latest episode. Okay, so and I will just sum up my talk. So we have made a study of 21 centimeter forest in the close proximity to quasar. As far as I know, that was the first one. Anyway, we have found out that, like I said multiple times, 21 centimeter forest in the close proximity to the quasar is sensitive to the integrated lifetime of the quasar. So therefore, it might be complementary probe of quasar lifetimes, let's say, to the Lyman alpha forest near Zone, And therefore, if you manage to measure this or observe this, there might be a new opportunity to constrain the supermassive levels root models. So thank you for your attention.
Thanks for that. I have a question. I'm an observer. So, what instrument do you need to be able to do that? And what, I'm just not clear what band you need to look at. From 21 centimeter down to what frequency you need to do.
Okay, so it will be around, if you are looking at redshift 6, let's say that will correspond to around 20 megahertz. Some I guess few megahertz bandwidth should capture the couple of megaparsecs there. So that's that. And I'm currently working on a project where we look at trying to push the observations or exploring the prospects of detecting the 21 centimeter fluorescence. Currently, it seems that UGMRT is our best bet currently at these frequencies. But of course, SK will be better, right? So we all look forward to that.
And things like so far.
So just give me a second, just to remind myself. So they have similar sensitivity around these frequencies. I know at redshift 6, UGMRT is better, but at redshift 7, sorry, I just don't want to lie here, so I can get back to you after I check some numbers here.
Okay, next question here.
Hi, thank you for a very nice talk. I wanted to ask if you have some selected targets that you would want to probe your theories at, some quasars at redshift, 6 and higher?
Yes, so currently there are 35 radial out quasars at redshift 5.5 that I know about. That includes Sylvia's laser. So those would be nice to target, but what I had in mind for a while now is maybe to at least look at quasars that are radial out, and if we have a measurement of the iron Lyman alpha for that, that would be, then you would actually see maybe some complementarity there. So that would be nice to do. But there are some quasars that are around 60 or 100 millijoules via 150 megahertz frequency. So those would be nice to target, brighter, better.
Thank you.
Is there anything to be learned from other combination lines like H alpha in the vicinity? You can get things here.
Or I don't know. I have not considered any of these.
Okay, well maybe let's think about it. Great, let's thank Thomas again. So then, as mentioned, Luigi is the baby, so he's flying right now to Japan. His talk, which was scheduled right now, will be, we'll just put it on the